So hello, Scalar. Thank you for staying around. I know it's been 2 long days of conference. I had an amazing time, met a lot of people. I really missed that. Last time I appeared in public was 4 years ago at this very same stage. So it's a pleasure to be back at this beautiful conference. Thanks a lot to the organizers for making this happen. My name is Gabriel, and today I'll talk about functional event-driven architecture, which is the title of my latest book. But before we continue, some of you might have seen it on Twitter, or if you're not on Twitter, I'm going to run a raffle at the end of this talk, and I'm going to give away a paper copy. All you have to do is just go to this repo, give it a star, and I have a little Scala CLI program written in Scala that actually fetches the stargazers from the GitHub API, and it picks a random winner. So I'm not going to be able to show that on in the screen, but trust me, I'll run it on my laptop and see who is the winner. Yeah, and I just have to show you that I actually have a copy to give away here. So here's the book. I only have one, so unfortunately, there's not many. But yeah, functional event-driven architecture, that's the title. Let's start by defining what event-driven architecture is, and then later we'll get into the functional part. So it consists of event producers and event consumers. We saw that earlier today in Alexander's talk, so thank you, because he introduced a lot of concepts that I didn't want to get from scratch. In this case, the message broker is Apache Pulsar instead, but it could be Kafka, it could be RabbitMQ. All these concepts are very similar across different brokers. So the concepts in this book actually translate to Kafka pretty well, and there is a lot of overlap in terms of terminology. But this book actually picks Apache Pulsar because it's my preference, and there's a lot of patterns that this architecture enables. By decoupling producers from consumers, you can have multiple services potentially across company boundaries. Sometimes you need to integrate with external teams. And we're just giving them events on a topic that they could actually consume and do something about it by reacting to events. This enables a lot of scalability and low latency, high parallelism, and a lot of fancy words. But it also introduces a lot of challenges. And we're going to have a quick look at some of those challenges and benefits that this architecture introduces, which is not new, by the way. But most of the time, and arguably the most interesting part of writing code in this type of architecture is it happens on the consumer side, where you need to deal, you need to do some event processing. And there are some well-defined patterns in the industry for event processing. The first one is simple event processing, SEP. And a quick example could be consuming an event, do something about it, like writing some of its attributes into the cache, perhaps publishing further events, and then move on to the next event. So we look at individual events and do something about that, but there's no connection between the other events, right? Once we process that event, then we move on to the next. Conversely, complex event processing, CEP, here's an example where you look at a much bigger picture. You just kind of like look at a snapshot of events. And here's a quick example. You consume a bunch of events, and you look for patterns in those events, and you can aggregate them in memory. And usually this is done in a stateful way. And for example, you want to process over a time window, which was also mentioned earlier today. The last one is event streaming processing, ESP, which is pretty much similar to complex event processing, except you're ingesting those events into an external data streaming platform, like Kafka Streams or Apache Beam and any others. But today, given time constraint, we're going to just have a quick look at the first two. And that's where we're going to see the functional part of functional event-driven architecture. So let's assume we have this very simple use case where we have user events, a register case, and a deleted case. This is all written in Scala tree. both of them have the same properties, event ID and user email, but we are omitting a lot of metadata from the event, like the timestamp, and just for simplicity. So bear with me a little bit. And there are many ways we could model the simple processing of this event. In this case, one of my preferences is just to define an engine class or a case object, whatever the case. When it takes a dependency, a class is the way. And in this case, it takes a user cache, and it defines a function from user event to f of unit, pattern matches on those events, and it does something, and it performs some action regarding that cache. So this is not very exciting. It's a pretty simple use case. There's not much going on. There's not even type class constraints here. But what we haven't touched into, but it's something that, thanks Alexander again for diving into committing offsets. And then another name for offsets commitments is also message acknowledgement, which is a mechanism used by Kafka, Pulsar, and other message brokers just to let them know when a message was successfully processed. Not only consumed, but it's successfully processed. And here's a very naive example where we have a function representing an ACR, which let us acknowledge that particular message back to the broker, right? Assuming that this message is an envelope that knows about the offsets of the broker. And here are where things get really interesting, because these are the things that we start asking ourselves the hard questions and start finding out that it's not as easy as we thought at first, because you might just write this code, call it a day. It works 99% of the cases, but when it doesn't, we're in trouble. And one of the examples here, right? We pattern match on the events, and we still perform that cache action, for example, registering the email, and then we acknowledge that message. But what happens if after registering that user email, the service crashes or that acknowledgement action actually fails because usually it's a TCP call over the network? And it's an interesting case because you start thinking about that, and that's when you start getting into message delivery semantics, and in this type of architectures, you usually go for at least one semantics. That means that we're going to have to deal, like, what happens here if the acknowledgement fails? Pulsar will redeliver that message at some later point in time, and that means that we're going to have a duplicate event. So how do we deal with that? And then these are the questions that we ask in the book, and we try to answer them. And usually one of the best options is just to acknowledge and accept the fact that we're going to have to deal with duplicate events, but make our actions idempotent. So it doesn't matter how many times we register the same email, the outcome is going to be the same, and eventually the acknowledgement will work. That's one potential solution, but it is not always possible. So we discuss all the details, and you can imagine this is a very, very simple example, but in a distributed system involving many services, things get really complicated quite quickly. So all these patterns are things that we discussed. But yeah, moving on from this example, let's look at how the entry point may look like. And here's, I use cuts effects and NFS2 stream that were featured today quite a bit, and really nice talks. So assuming we have a bunch of resources that we initialize in a streaming context, here we have an HTTP server, an events consumer, and the engine we just saw previously. So we run that server forever while concurrently we consume events, and we run them through the function that we defined in the previous engine. And here we use eval map to do so, but there are a few other methods like par eval map or par eval map and order that we could leverage depending on the semantics we're looking for. So this is something really fun to play around with. But that's simple event processing. Now let's look into complex event processing, which is the most fun actually. And in the book, I'm fascinated by finite state machines. And finite state machines are simple, probably a fancy word, by encoding this function, which is a tuple that takes a state and an input, and it returns a state and an output, potentially within a context F. And we don't care about that context F. We can use the ID monad from cats, so we don't have to actually declare what the effect type is. And this plays really, really well with FS2 streams. These are two of the methods defined by the FS2 streaming library, omitting variance details for simplicity. Well, you see, map accumulate, it takes an initial state, and then it will continue running repeatedly that function over the fsm.run. It will call fsm.run repeatedly. That's when you don't care about the context, and this is when you have some effectful computations. And I'm really fascinated about this, and a couple of years back I wrote a blog post about how these two match, and it's a match made in heaven, and this is the way. And so in this blog post I dive deeper into all other more complex examples if you want to have a look, but also in the book is something that appears quite a lot. So, equipped with that knowledge, let's just have a look at a quick example involving this the finite state machines and FS2 streams. Imagine we have these 3 different cases of price event, again omitting the metadata details from the event, and then we define a price state data structure, which just it has a map of symbols and price history. So every time we receive an event that contains a price and a timestamp, we're just going to be aggregating that in memory. So these are the data structures, and here's how the processing looks like. This is stateful processing, and it will aggregate things in memory, right? And in this case, we don't care about any effects, so we use the ID monad for that. And this is just pretty standard, pretty simple. It's just an FSM is basically a function that you can unit test very easily by feeding a state and an input and running expectations on the outputs. So here when we pattern match on the state and the events, and when we get a created one, we just initialize the price history here. When we get the updated one, we add that to the price history and update the state, and when we get a delete symbol, we basically remove it from the state that we aggregate. Now, this is not particularly interesting. What we are doing here is it's very trivial, and we shift the whole responsibility to the caller. So whoever is the caller of this fsm.run will need to be responsible for keeping track of the output state and feeding it back into the state machine and taking care about resetting that state at some point. But we can also shift that responsibility into the finite state machine itself. And here's an example of how to do that. Let's say that we want to process these events, aggregate them in memory, and we're going to be looking at them over a time window for 5 seconds, and when we are done, we publish those alerts. That's why we define this interface here. And in the implementation of the price alerts, we could do whatever. We can just filter out symbols we don't care about. So that's up to the interpreter. But back to the FSM definition. Here we have a class price engine that it's defined over an abstract effect that requires to be an applicative, so we no longer use the ID monad here. And the pattern matching, it's pretty much the same, except we use pure.f here, f because it's an abstract context. But the interesting part is right here, is the input type changed from price event to either price event or tick, which is representing Scala 3 union types. So all the pattern matching of the events are pretty much the same as in the previous slide, but the tick here is the interesting case. Here's where whenever we get a tick, we publish whatever we aggregated in memory, and we reset the state. Now, from the caller is going to be responsible for sending this tick every 5 seconds if we want to aggregate that over 5 seconds or over any configurable time. And how will that look like from the entry point? We will have a function runner, something like this, where it has a stream of I/O or either price event or tick. And what we're going to use is that method we saw before from FS2 stream called eval map accumulate. We start with initializing that price state, and then FS2 is just going to run this function from the fsm.run continuously. And an FS2 stream represents potentially infinite data, so this could run forever or until the service crashes. So how do we get to this, right? Actually, the stream of price events or ticks, because it's not something that you see on every day, and it's very simple. Here's how you can create ticks using stream.fixedDelay over time window of 5 seconds in which it's generate ticks. In Adam's talk yesterday, there was some similar case where you generate ticks over a stream. And assuming we have a stream of price events, which is the case when you use Apache Pulsar and you consume these events, you can get this stream. All we need to do is just call merge, which is defined in the FS2 stream library, and it doesn't require any type ascriptions whatsoever. It just works, and so this is pretty cool. And then we get that union type. Scala tree is smart enough to understand that this is the expected type. So this kind of like pattern appears in a few of the services that we develop in the book. So recapping, we saw an example of simple event processing, where we only look at individual events at a time, and complex event processing, where we look at a bigger picture and using time windows as an example. But it's not all we do. We not only talk about event processing, but there are many other patterns that appear in this book. One of them, and one I like and that we use at work, is the Outbox Pattern. And here's the problem that it solves, that you haven't heard about this pattern. Assuming we have this HTTP service which allows us to register authors, and when we get a request, we try to persist that author information, the record, into PostgreSQL. We also like to register that author's name into Redis, just for quick lookups. And once we're done, we publish an author-registered event into Pulsar. But the problem here is that we cannot guarantee atomicity. We have 3 different I/O boundaries here, and we cannot. It's like virtually impossible to guarantee atomicity. Best we can do is probably using something like the Saga pattern. But the Saga pattern has its own drawbacks as well, because rollbacks could also fail, and we cannot guarantee atomicity anyway. The Outbox pattern solves this issue in a very elegant way. And here's how. Instead of doing all these 3 actions separately, we are gonna, it looks back into computer science back in time and say, why not leveraging database transactions? They've been around longer than since I was born. So, and so here's how it goes. We register the author into an authors table into the database, but we also try to write the event that we want to publish eventually into an Outbox table, and this happens within the context of a database transaction. And there's this concept of a CDC connector. CDC stands for Change Data Capture. It is a technology that's been growing in popularity in the Java ecosystems in the last couple of years. And there's Kafka Connect in the Kafka ecosystem, but there's also Pulsar IO in the Pulsar ecosystem, and there are many other third parties as well. So here we assume that this is responsible for actually reading the write-ahead log from Postgres, from the Outbox table, and every time it detects that there is a new event inserted, it will just publish that into a Pulsar topic that we configure. So from here, what we can do is just consume these author-register events from the same service and then perform that action that persists the author's name into the cache, or it can be a different service, that's depending on the case. So this is a very elegant solution, but it's not perfect. It doesn't fit all the cases, so this is something that you need to analyze. And one of the drawbacks that are very evident by looking at this diagram is that we make the database the bottleneck. And if you have a huge ingestion of events, you don't want to make that database a bottleneck, because it's one of the problems that event-driven architecture tries to avoid in the first place. But it really works well when you don't have such a big amount of events and strong consistency is desired. And so this is something we discuss in some of the examples in the book. And there are many different patterns in distributed systems. And I think this one was one of the coolest to showcase, because it's quite trendy in the Java ecosystem these days. But last but not least, what I what I think it's very, very important to understand whenever you pick a message broker, and either whether that's Kafka, RabbitMQ, Kinesis, if you use AWS, or Apache Pulsar. It's just to understand its pros and cons, how it compares to other brokers, and actually try to understand the important concepts. And Pulsar subscriptions is, in my opinion, the most important concept to understand. It's like the first thing you need to learn. And it's basically how subscriptions and consumers interact with each other. And it supports 4 different types. The first one is an exclusive subscription that allows only a single consumer at a time to attach to that subscription. And a subscription actually reads from a topic. So the offsets work differently than in Kafka, but it's a pretty similar concept. And a failover subscription, multiple consumers can attach to that subscription, but only one at a time will be receiving messages. That will be picked as the leader, and in case it goes down, then Pulsar will pick up another leader from the ones that are currently attached. A shared subscription is where multiple consumers can actually attach to that subscription, and messages will be delivered in a round-robin fashion. And key share subscription is similar, except that we dictate how events are distributed across consumers, usually by indicating what is the ordering key or partition key. And just to finish this talk, here's a quick diagram without much context, but this is one of the services that we developed in this book, which is a WebSockets client, and it used this concept of ephemeral subscriptions. This is something that I used in production 3 years ago at a company where I was using Pulsar for the first time. And it seems to scale pretty well. You can create ephemeral topics and ephemeral subscriptions. And here's the general idea. We have a WebSocket client that actually in the book is written using Tyrian, but also Elm. And you can run either of those from the client. You have a nice UI. Once you subscribe, you connect to the WebSocket server. Here we have WS1 and WS2 representing 2 different instances of the same service. You get assigned that socket ID, which is a UUID, and that will actually create a subscription using the very same ID that we get from the WebSocket client. So there's a one-to-one mapping in there. And once that, we call it ephemeral subscriptions because WebSocket clients come and go. If you close the tab, close the browser, then they disconnect, and that subscription will be scheduled for garbage collection at some point. So I'm not going to dive into details in this one because there's a whole chapter only about this, and it gets really interesting. We discuss scalability issues, what happens when there is consumer rebalancing, why a subscription would work or why a subscription wouldn't work. I mean, a subscription type from Pulsar. So yeah, I encourage, hopefully, this give you a little bit of context of what we actually go through in this book. I try to make it as practical as possible. It's a different type of monster, like compared to the previous book, where you just basically a single service writing to the database. This is completely different. So hopefully you find it useful, and that's all I had today. The project. It's there, the project that supplements the book. And here's the link to the digital book and the paper copy. And I have one book to give away. Unfortunately, you're not going to be able to see it, but trust me, I'll try to run that. But thank you.
Thank you, Gabriel.
Do I have time 2 minutes to run it?
Yeah. Do it, and in the meantime, maybe we have some questions. Anyone? Yeah, okay. So, can you run it and answer the question at the same time?
Yeah. This is basically just, I wanted to show you all, this is GitHub Actions running the raffle and picking up a winner. You're probably not going to see it because it's very small, but but it's just running here, and the winner will be posted on this G Volpe /stargazers-raffle is on GitHub. And if you go to the only issue open, oh, this is not going to work now. I need to, hold on. I need to unlock the conversation here. Hopefully in time. Okay, hopefully that works. But if it didn't, paste the winner here, it will still be in the logs of the GitHub action. So it's running there. Give it a minute. Yeah, what's the question in the meantime?
Oh, I want to clarify if you can go back to the Outbox pattern.
Yeah.
Yeah, so what's actually happening with the CDC connector? So you're writing a new row to a particular table, and then that is triggering something in the CDC connector. What's going on there?
That's a change data capture. Is a technology that there are. It's very, very, very well known in the Java ecosystem, but Scala. Sorry, I have to interrupt you. I will answer your question. Don't worry. But we have a winner, and it's Wodek Kleszcze. It's somewhere here. Yeah. So please come on over here. I'll give you the book. So there were 97 stargazers of this repo, and his name is Piotr Jusiak. Jusiak, is that correct?
Is that correct?
Perfect. Congratulations. And, yeah, no, but that's a fun, right? It was just a raffle. Congratulations.
Thank
Here's
you.
the book.
I'll definitely read it. I can promise you that.
Okay.
Okay.
Anyway, back to the question. Yeah, so change data capture. There is a whole ecosystem of Kafka connectors. It's called Kafka Connect. In Pulsar, it's called Pulsar IO. And so this is something that you can just look at the documentation and see what data stores are supported. There's also Divisium or Divisium, I don't know how it's pronounced, that it's pretty popular for Postgres, and it has a bunch of supported sources and sinks and connectors. And the example, I mean, in this repository that this is the application that supplements the book, there are examples of that specific pattern and the change data capture and how to actually run that connector using Pulsar. Does that answer your question?
Oh, I guess I have to read up about it more. I was just curious, how does writing a new row to the table, how is this information communicated to the CDC connector?
Very good question. Yeah, that's actually a technology that it has to be implemented by the data store. So this is something implemented in PostgreSQL, but also in other databases. And PostgreSQL, the mechanism they use is writing. They have a write-ahead log, WAL, and that's where the C connector is pulling data from. It actually recognizes that the new record has been inserted, and CDC actually can detect whether it has been inserted, updated, or deleted. So on the CDC connector, you can act upon those three different scenarios and write your logic there.
But then there'll be a scalability bottleneck in SQL.
Well, that's the drawback of the Outbox pattern, right?
Oh, thanks.
No worries. But it's great when you desire strong consistency, so semantics. Any other question? Yeah.
Okay, we have one up there, so it's going to take us a moment.
I can drink some water.
Thank you, Gabriel. The talk has been very inspiring.
Thank you.
Every time I have done event sourcing, I use the Akka ecosystem. So one of the aspects that has been more challenging, at the same time more interesting, is like defining a strategy for recovering from a disaster. In that case, I'm very used to use Akka persistent and Akka persistent query to preserve like the state of the actors, and that way I can recover from the snapshot journal strategy. There is another problem is when the model evolves, I need to adapt the model that have been persisted in order to be able to recover a previous state. So what, in that matter, what in your book are you including like a solution for these kind of problems?
Yeah, we discussed, it's a very good question. Actually, akka cluster, akka persistent is featured in the book as one of the potential solutions. You have clustering, and the responsibility of managing that cluster is shifted into the developer itself. But when you pick this type of architecture and rely on Kafka or Pulsar, you shift a lot of the responsibility to that monster that is a message broker that needs to be tamed as well. And there is a blurry line between DevOps and developer experience there. But yeah, that's something that we definitely discuss, recovery disaster, and there's one service that is actually called snapshots. So that probably gives you a hint that we actually get into snapshots and similar to what akka persistence does. But yeah, happy to chat afterwards a little bit as well in details, but it's also hopefully very little in the book as well. Hope that answered the question.
Thank you so much.